All right. Well, I'm really excited to welcome Athena Nghiem to give us our first keynote talk today. Athena is an assistant professor at the University of Wisconsin-Madison. The title is up there. I won't read that. For context, one of the things that we try and do in these meetings with our keynotes is we try and invite scientists who are working in fields that are not immediately within rock and paleomagnetism, but are very much adjacent to what we're all trying to do. And the idea behind these talks is that they're meant to foster new ideas within our communities and potentially new collaborations with keynote speakers as well. So with that, I'm going to open the floor for Athena.
Okay. Thank you so much for the introduction, and I'm very excited and honored to be invited here today to share my research, and I'm really looking forward to meeting some of you over the course of this meeting and learning more about the magnetism community. And today I'll be sharing my work on dynamic iron redox transformations and their impact on contamination in groundwater. So a lot of motivation behind my work is on groundwater. And as you may know, groundwater is a source of drinking water for an estimated 2 billion people around the world. However, as you might also know, groundwater can be contaminated by naturally occurring or geogenic contaminants, such as trace elements like arsenic. Some of the health effects that occur from drinking arsenic-contaminated water include many adverse health effects, such as multiple types of cancer, cardiovascular disease, neurological development issues in children, even when consumed at low concentrations. And here you can see that groundwater with arsenic above 10 micrograms per liter, which is the World Health Organization guidelines, as well as the EPA maximum contaminant level, affects an estimated 94 to 220 million people around the world, with the largest proportion estimated to be in Asia. So a very simplified background schematic on how arsenic is released in groundwater. For example, across the deltas of South and Southeast Asia, arsenic, as I mentioned, is geogenic or naturally occurring in rocks. In very simple cartoons. Some of these include pyrite or arsenopyrite, which just has arsenic associated with it. And then you have weathering, which transfers arsenic onto the surface of iron minerals. So we'll get into our iron minerals more later on. But essentially, you have things that occur, such as pyrite oxidation, releasing dissolved arsenic, and then this arsenic gets sorbed onto your secondary iron minerals. After this process occurs, sediments with arsenic are transported and deposited by rivers, for example, across the great deltas of South and Southeast Asia. And after their deposition, they undergo alteration in the anoxic subsurface. So in another very simple cartoon, in the anoxic subsurface, you might be familiar with microbes such as iron-reducing bacteria. And as you go down the microbial redox ladder, of course, the microbes start to use oxygen for their energetics, and then nitrate, and so on and so forth, until you get to your iron minerals, to which the arsenic is sorbed. And then iron-reducing bacteria couple the oxidation of different types of organic matter to CO2, and then reduce your iron 3 minerals to dissolved iron 2, thereby releasing arsenic into solution. So of course, this is a very simple cartoon. You can, of course, add more complexity, and this really shows in the variability of arsenic in groundwater, which is influenced by multiple factors, which I'm already simply summarizing here, but things like hydrogeology, of course, our mineralogy, all different biogeochemistry that can occur. I tried to add some more complexity in this cartoon. Of course, you can have different aquifer compositions, subsurface stratigraphy, different solute compositions, so competitive sorption for surface sites on iron minerals, and of course, our iron mineral transformations, which we'll get into shortly. So this really creates large variabilities at many different scales. And to get a sense of this variability, here you can see a compilation of groundwater arsenic that has been compiled as part of a USGS Pell Center working group. So this data comes from different field studies, geological surveys, and these points represent aqueous concentrations of arsenic. So anything that's not in this kind of darker blue color essentially means it's above the World Health Organization guidelines of 10 micrograms per liter. So you might look at the maps and you're saying, oh, there's a lot of blue. It's not too bad. But when you actually zoom in on scales that are more relevant for water usage, so here let's zoom in on Vietnam and on the Red River Delta, which is in northern Vietnam, and on the scale, basically the kilometer scale that's actually relevant for household water usage, you can see that there's this very characteristic spatial heterogeneity in the arsenic concentrations in groundwater. So essentially what this means is your well might be very low in arsenic in groundwater, but your neighbor's well might be very high in arsenic, which just showcases this variability that can occur. Of course, you might also look at this map and say, oh, this is actually in 2D, so maybe it has something to do with depth, of course, because all groundwater wells draw water from a certain depth. So to take a closer look at that, let's zoom out a little bit and now go over to Bangladesh. So we can see that this spatial variability also exists with depth. I think there's another rotation going on here. Yes, so there's still some variability in our arsenic concentrations, but we start to see kind of this trend in the concentrations with depth. And when we take a closer look, we could see that a lot of high values of groundwater arsenic are in the shallow aquifer system, while a lot of low values seem to be deeper in the aquifer system. And the same is shown on the left-hand side in this core profile, basically looking at dissolved aqueous arsenic concentrations down a well. So why is this? Well, actually, it was discovered that this difference in arsenic concentrations is associated with sediment age. So here I'm still showing you that dissolved aqueous profile, but now we have a core next to it. And essentially, there was this kind of finding that higher groundwater arsenic was associated with younger Holocene-aged sediments, while this lower and deeper aquifer here, the lower groundwater arsenic was actually associated with Pleistocene-age aquifer sediments. So interestingly, this is important not necessarily because of the age of the sediments itself, but actually, as we know, because of the redox state of the sediment. So, and our iron mineralogy. So our Pleistocene aquifers contain more oxidized sediments, while our Holocene aquifers typically contain more reduced sediments. So for example, if you drill into a typical Pleistocene aquifer in Southeast Asia, you might find these orange sands, which are typically indicative of your iron 3 minerals. Meanwhile, if you drill a well into a Holocene aquifer, you might find these gray sands, which are more typical of iron 2 minerals. And this distinction is not so important because of the sediment age, but actually because of the redox state of the iron mineralogy in the sediment, and then its association with groundwater arsenic. So in your orange sands, you expect there to be low arsenic. Arsenic still sorbed onto your iron 3 minerals, while in the gray sands, you would expect there would be reduction occurring and high arsenic. So just a brief background on, maybe you're thinking, why is there this dichotomy between the Pleistocene and Holocene sediments? Well, it was suggested that sediments that remained following the last sea level low stand during the Pleistocene either became oxidized, and then their arsenic content was either immobilized via sorption onto the iron minerals, or it was removed by meteoric water, kind of flushed out after deglaciation. Okay, going back to our iron mineralogy. So this means that certain aquifers are assumed then to be safeguarded against arsenic contamination due to your abundant oxidized iron minerals. And this means that people commonly rely on aquifers with oxidized minerals that are believed to be less contaminated as a very cost-effective method to reduce exposure to arsenic. So for example, in Bangladesh, maybe they would aim to use the deeper, low arsenic aquifers. So in this scenario, if you have your well low in arsenic and your neighbor has their well high in arsenic, maybe your neighbor drills a different well and they find it's low in arsenic and it's good, or you share your well water with them and now they also have reduced their exposure to arsenic. But another thing missing from kind of this snapshot is that these arsenic concentrations are only a snapshot in time. So this is only one measurement at one time where the groundwater arsenic was measured. And actually, when you think about it, where low arsenic groundwater is available, the sustainability of these uncontaminated waters is being jeopardized. So what happens if these low arsenic aquifers become high in arsenic? And that's one of the motivations behind my work, is to investigate this question. What happens when these low arsenic aquifers turn into high arsenic aquifers, either in the past or due to perturbations that are happening nowadays? And to answer this, as you already know from my title, we can look at iron mineral redox transformations. So in this picture, our aqueous measurements are only half of the story. And the other half, we need measurements of mineralogical transformations that can help us describe the processes that release or trap arsenic. And this is the motivation behind my talk, and of course the research in my group, which is posing the question, can we identify changes in aquifer sediments releasing arsenic due to these active redox processes that are occurring? So for this story, I'll take you over to Vietnam. And this field site is in a village just south of Hanoi, Vietnam. So Hanoi is up there, and here's the little satellite image of our village in the corner. Something really interesting about this village, now we're gonna get into hydrology a little bit, is that the city of Hanoi has been rapidly growing, experiencing a lot of population growth. So there's been really intense pumping there by the municipal water supply, and this has changed groundwater flow patterns. So those contours that you see up there are examples of groundwater depression cones, and essentially in this satellite image of the village, what used to occur was aquifers would discharge into the Red River, which you can see the meander of here. But now what's happened because of this intense pumping by Hanoi is that the groundwater flow direction has reversed. So a lot of the river water is now infiltrating into the aquifers in this region. And these kind of balloon points you see, the red ones mean it's high in arsenic concentration, while the blue, again, is low in arsenic concentration. So if we look at a transect of this field site, actually contamination of a Pleistocene aquifer was previously identified. So in this transect, here we're seeing color, kind of like how I mentioned to you, orange versus gray sands, but actually these are now diffuse spectral reflectance measurements, which also show you similarly orange versus gray. We have a Holocene aquifer adjacent to a Pleistocene aquifer, and when we compare this with groundwater arsenic concentrations that were measured, we actually find in the Pleistocene aquifer that there's high arsenic there, which is 10 times the World Health Organization guidelines. So sometime, this Pleistocene aquifer has undergone these iron mineral transformations and has now been releasing arsenic. So this made this site the ideal site to investigate our redox transformations, which caused this formerly uncontaminated aquifer to undergo reduction and then release arsenic. Okay, so how do we approach identification of iron minerals? Of course, we can do it visually, like when you're at the field site, taking a look at the sediments, and also these diffuse spectral reflectance measurements, as I mentioned. Another thing that was identified at this field site was the ages by radiocarbon. And what was found was that, of course, not all the gray sands were Holocene, but actually some of them were Holocene, yes, but some of them had been Pleistocene age sediments, but now have turned gray. So originally they were our orange oxidized iron minerals, and now they've undergone reduction. So the goal of this work was to even better distinguish these gray sediments to indicate which redox processes cause changes in these presumably previously pristine aquifer. So just a reminder of the increase in arsenic that we expected. Then the next goal was to kind of upscale and predict sediment redox state in similar environments where sediment data is sparse using machine learning, because we all know how expensive it is to get a lot of cores. So we want to use another data set where we could upscale the relationships, and aqueous data, especially groundwater data, while hard to collect, is a lot easier than drilling everywhere. So the approach that we took is to drill cores in the field along this lateral transect, and then we took subsamples of the cores at depth and preserved them for redox analyses. So here you can see our transect locations and our core locations along our transect. And the approach that we take, and maybe the approach some of you also use here, is X-ray absorption spectroscopy. So this snapshot is from Stanford synchrotron radiation light source, and we collected iron extended X-ray absorption fine structure, or XF spectra, at the beamline, which provides information on the local structure. So here's an example of one sample at a certain core location and a certain depth. And a brief review for those of you who don't think about X-ray absorption spectroscopy all the time. So essentially, when you're at the beamline, you have X-rays. If you're focused on a certain element, for example, like iron, when you shoot these X-rays at your sample, the X-ray is absorbed when the energy of the X-ray reaches the binding energy of the electron, which is a function of your oxidation state and structure. And this photo electron energy depends on the binding and excitation energy of the orbital from which it was derived. For example, the K edge. So this is an example of an iron kind of spectra that you would get. On the x-axis is energy, on the y-axis is normalized absorbance, and you have this characteristic jump and kind of up to higher energies, this other part of the spectra. So the jump is actually the white line intensity, or the edge jump, and it's called the X-ray absorption near edge structure, or ZANES, and it's representative of the transition of the core electron to high unoccupied energy levels. And kind of the part of the higher energy is the X-aps region, or the extended X-ray absorption fine structure. So this is kind of post-edge region. But now this is the same thing, just with some equations in wave number space. And this X-aps region represents the sum of the scatter of the photoelectrons, photoelectron waves. So essentially it tells you kind of what your bonding environment is to iron in this case. So once you collect a bunch of this spectra and pull some all-nighters, then you can get your spectra. And then one common approach is just to do linear combination fitting. So you have different standards that you know well, and you also have the spectra of, and then you just fit that to your sample spectra. But the approach that we wanted to take here, because we were analyzing a lot of spectra, was to do a data-driven approach to spectroscopy. So we collected all our spectra, but then we first performed principal component analysis to kind of look at the data all together, and then kind of from the principal component analysis, perform hierarchical cluster analysis to see if we could define different groups of the redox transformations that were occurring. So first, when we take principal component analysis, we took all the spectra, all the samples, which is, again is a core at certain depths, and then we get our principal component loadings, and then we can kind of take a first look to see what this means. So here, for some principal component results, on the x-axis, we have principal component loading 1, which explains 71.6% of the variance in our data. On the y-axis, we have principal component loading 2, which explains 9.4% of the variance in the data. And each of these points is a sample colored by the field classification that I mentioned. So gray holocene, orange pleistocene, or this gray transition that I mentioned. And in the blue points are different iron standards. So we already start to see some interesting separation kind of in this figure. If we look at more positive values of the principal component 2 loading, we see a lot of our oxidized iron oxyhydroxide minerals there, like hematite, ferrihydrite, goethite, magnetite. And towards the more negative principal component loading 2, we see different more reduced iron 2 minerals, sulfides, silicates, also siderite. So there starts to be this separation. And it also looks like it kind of separates by our different field classifications that we've assigned. So this kind of motivated our impetus to do cluster analysis to see what the data would tell us about how it would organize itself in this space. So then to do hierarchical cluster analysis, instead of taking all the principal components, we only took the top 4 principal component loadings, because as you can see here, the top 4 principal component loadings explained up to 90% almost 90% of the variance in our data. So taking that, now we can do our cluster analysis and create this kind of tree diagram that I'll walk you through. And for those of you not as familiar with hierarchical cluster analysis, it's an unsupervised method, meaning you don't tell the data how to group. It just will group itself based on statistics kind of into these tree diagrams. And the closer things are together in the tree diagram, the more similar they are. And the further apart they are, the more different they are. So I'll walk you through the result here. So if we look at this tree diagram and we start in the center node, and this is just colored by the clusters that come out, we see that cluster 4 comes out first of the central node. And then if we go back to the central node, we see there's another node where cluster 1 comes out, and we go back, and cluster 2 and 3 come out of a shared node there. So this is, we didn't tell it what groups to group into, but now we can compare it to the groups we know or have previously defined. So this is our field classifications that we had before, and now I'll put it together for you so you can see what it looks like. So I'll walk you through this, but essentially we found that our unsupervised cluster analysis distinguished between our Holocene and Pleistocene sediments, including varying arsenic releasing redox states. So to slowly walk you through this, again, we start at the center. We have this cluster 4 branch off first. We see it's mostly all composed of our gray Holocene sediments. When we go back to the center, we see that there's these 3 clusters that come off. Cluster 1 is primarily all our orange Pleistocene sediments. And we go down to cluster 2, which is also orange Pleistocene sediments. And we go to cluster 3, which mostly seems like our gray transition Pleistocene sediments. So it's interesting in this cluster 3 that the ones that we did identify previously via spectral reflectance or in the field as kind of this gray transitional sediments do fall in this bin, but there's some that we had previously misclassified. But the mineralogy is telling us that it's most closest to these gray transitional Pleistocene sediments. So it's kind of stronger than our error-prone previous classification. Maybe some adjacent samples are a meter above or below, for example. And then we also see that cluster 2 and cluster 3 share a node, which indicates that the cluster 2 sediments are more similar to cluster 3, even though we had only characterized them as our orange Pleistocene sediments. And again, this is important because of its association with the groundwater arsenic. So if we review the associations going counterclockwise, we have our orange Pleistocene sediments expected to be low in arsenic. Cluster 2, now we call this our orange transition. Maybe there's some activity going on in the iron mineralogy in the sediments that's not yet apparent in the groundwater, but is apparent in the mineralogy when we measure it. Cluster 3 is our gray transition sediments, which are expected to have high arsenic, and of course our traditional gray Holocene sediments, which indeed do have high arsenic. Okay, so now that we've done that approach, we can still go back and do the traditional approach to kind of tell us the story of what mineralogy is actually changing. So again, we have our linear combination analysis. We use 10 standards: ferrihydrite, goethite, hematite, green rust sulfate, magnetite, some mixed iron 3, iron 2 silicate, biotite, siderite, mckinnowite, and pyrite to fit our samples. So as you fit the spectra, you will just get fractions of different proportions of these minerals. Okay, so what does this result look like? Well, I'll walk you through this heat map, but essentially linear combination fitting shows the redox changes in each cluster. So across the top on the x-axis, we have our different clusters, cluster 1 through cluster 4, going from more oxidized to more reduced. And the color in each of these boxes indicates the average fraction in that bin. And on the y-axis, we have our iron minerals going from generally more oxidized to more reduced. And we can kind of start to see these trends that occur, including that the oxidized and minerals undergoing reduction are found in the Pleistocene cluster, and reduced minerals are found in the Holocene cluster. So specifically, for example, we can take a look at ferrihydrite. So when we look at ferrihydrite, our very amorphous Iron 3 mineral, we can see that it decreases from the more oxidized clusters to the more reduced cluster, suggesting that our ferrihydrite has undergone reduction. We can also see, for example, in cluster 4, which is our gray Holocene sediment, contains more reduced minerals such as siderite, which forms after extensive reduction from iron 2 and from bicarbonate. And we can also see that biotite is also greater in cluster 4 and other silicates in the fourth cluster, the gray Holocene group, because biotite has undergone more weathering in the Pleistocene groups, clusters 1 through 3, over time. So this is just a snapshot which shows you the averages, but you could also look at the histograms of the linear combination fitting, and it also tells you a similar story. So this is kind of looking at the histogram, so you get more than just the average value, but still sorted into these 4 clusters. It shows the reduction and transformation trends in each defined cluster. Again, now we can see more closely how ferrihydrite decreases. We can see maybe some goethite forming, changes in hematite, potential formation of green rust, and maybe transformation to magnetite in the transitional clusters. Obviously more siderite in our gray Holocene clusters. And this falls in line with kind of like the transformations that we know that happen in arsenic systems, but now defined by these clusters that came out of our analysis. So again, it's known for arsenic that you can have your amorphous ferrihydrite transform with aqueous iron 2 to goethite. You can have transformations to green rust and magnetite, or directly to magnetite. Siderite when you have a lot of your bicarbonate. So it's nice to see it verified in these clusters that we have defined across this transect. The other things we have, of course, are our silicates, and also maybe something it's hard to see here in our iron sulfide minerals. Maybe something's going on with mckinnowite. Separate to this work, I've also done a lot of studies into iron and sulfur cycling. If you're interested, I'm happy to chat more about it later, but there's also a lot of dynamics that can go on as well with the sulfur cycle and lead to neoformed sulfide minerals as well. But this is just one way to characterize your iron mineralogy, of course. And I'm very excited to talk and discuss more with you about different magnetic properties or other things we can use to define these redox transformations in these kind of aquifers, but also in bedrock aquifers, etc. So I'll be happy to chat after or during the course of this conference. But now going back to our original motivation, which was the groundwater, now we want to finally pair all these mineralogical observations with actually our aqueous concentrations. So now we can pair our sediment data together and take a look at what it tells us. So in these box plots, on the x-axis is still kind of those sediment-defined clusters that I mentioned, and on the y-axis now are different aqueous concentrations. So over there we have arsenic on the left-hand side, and on the right-hand side we have iron. And we indeed do see that the more reduced sediment-defined clusters have high arsenic and high iron concentrations in groundwater. So our gray transition does have high arsenic, so does the gray Holocene. Maybe the cluster 2, as I was mentioning, might have a little higher, but it's not statistically significant, probably. And we see that there's higher aqueous iron indicative of iron reduction. So as I mentioned, we don't want to only stop there with these relationships, but try to find a way to generalize these findings between our sediment and our aqueous concentrations. So this is where I built a model to predict sediment redox state from these aqueous concentrations. And essentially, this was done by a classification model. So I ran and cross-validated a supervise. So that means we're telling the model what the right answer is to classify sediments by these redox-sensitive aqueous measurements. So how this works is that from the data set I just showed you, I took the aqueous arsenic, manganese, which is also very redox sensitive, and iron measurements. I put it into a multinomial logistic regression model to predict kind of these sediment redox classes that we found. So our orange Pleistocene and orange transition, our gray transition, and our gray Holocene sediments. And then after this model was validated and cross-validated, then we can apply this classification model to our compiled databases of our aqueous arsenic, manganese, and iron concentrations that came from this working group that I had mentioned. So we take those aqueous concentrations, we kind of use that model, and now we can predict kind of these sediment redox states where we didn't have much sediment data before. So what does this look like? Well, as I mentioned, this model was based on a field site in Vietnam, so we can apply it to a similar environment, which is Bangladesh. And we see that the sediment classifications based on redox state and depositional history can be described where we had those aqueous measurements before. And when we compare it to maybe more traditional geology, our sediment classification of our Pleistocene clusters, which are the top two here, actually matches the previously identified Pleistocene terraces that exist in Bangladesh. So on the first order, at least on the very broad scale of country, it seems that our relationship can be upscaled. So now we can look at the same data. This is now colored by your aqueous arsenic concentrations again in the different bins or the different clusters. And we see that indeed high arsenic is found in the Holocene cluster and in the transition cluster undergoing reduction. But you still see there's a lot of low arsenic points. So maybe this classification could serve as an indicator of potential redox transformations that could lead to arsenic release. Maybe there are places where we should investigate more with field work, go to some field sites, or measure more arsenic concentrations than just once over time to test the wells. And this is important because using these results will help to navigate if these wells are at risk or will remain low for years to come, especially as I mentioned, since well switching is a very low cost measure to reduce arsenic exposure. So the main result of this work was that I modeled an approximation of the iron mineralogical environment from aqueous data that describes our redox state and kind of the depositional history of the region. And then we use this relationship to upscale to similar deltaic environments. The implications are that we have the ability to predict and identify areas potentially vulnerable to arsenic contamination based on this aquifer chemistry. And this is important, of course, for past changes that have occurred. Also, we don't know when that change in that transect occurred in Vietnam, so if someone has some good ideas, please let me know. But also current human-made perturbations such as groundwater pumping. So as we continue to rely on water resources, as they're becoming scarce, as we continue to pump more, this might cause similar changes in other environments. And also, these kind of techniques can be applied to other aquifer settings and other redox-sensitive contaminants and other trace elements, and also with other tools and techniques to identify iron redox mineral transformations. There's many, many other tools besides XFs, and I'm excited to learn more about everything available and from the conference this week. So as I mentioned, I'm not just limited to arsenic and quaternary aquifers, but this is just a snapshot of one of my PhD students right now who's focused on sources of molybdenum contamination in Wisconsin. I didn't show Minnesota on the side, unfortunately, in Wisconsin. So in southeastern Wisconsin, there's been evidence of molybdenum contamination. So molybdenum is kind of different from arsenic in that you need it at low concentrations, but it becomes toxic at high concentrations. And there's this argument in the literature whether molybdenum comes from anthropogenic sources, potentially coal fly ash reuse, landfills, or whether it comes from aquifers that this region relies on, including bedrock aquifers. So Savannah is doing an investigation of the sources of molybdenum. There's been different release mechanisms suggested associated, of course, with iron minerals and other similar carbonate aquifers in the US. So this is the beginning of this investigation that is starting in my group. And with that, I just have my acknowledgements for where I did this work previously, and of course, our collaborators in Vietnam without we could not do any of this work, all the synchrotron work that I and many others did, and the USGS Powell Center Working Group. And with that, I'm happy to take any questions.